Hello and welcome to lecture 20 in chapter 19 in our comprehensive course on AI, machine learning and data science. Now, as such, we want to start with this topic, hypothesis testing. But before that, just very quickly, I want to do one extra discussion about the previous chapter's last example. Right. So, in that chapter, we did this code as the last example that what is confidence interval. So, for the example of that, we took this kind of code, right? And we found that this is how the code was plotted. We took one gamma distribution as the population, and the shape, that is the standard deviation, was 2, and the scale was shape I think stands for mean perhaps, and the standard deviation is 2, and the number of observations are 1, 2, 3, 4, 5. So 1 lakh observations are there, right? And we want to demonstrate how to construct confidence interval. But I have now augmented the code so that it will now not only demonstrate how to construct confidence interval, but it will also demonstrate the central limit theorem. Okay, what the central limit theorem says, irrespective of the distribution of the original population, this is my original population, it may have this black colored normal bell curve distribution, or it may have this black colored uniform distribution where my cursor is moving, or it may have this kind of exponential distribution or any other distribution. But when I draw multiple samples from that large population and I find the means of all the samples, then those means are always plotted. When they plotted on XY axis, they are always distributed in that manner so that the curve passing through all means is always the normal distribution or the bell curve. So that means provided a few conditions are satisfied, such as the observations are independent. Second condition was that the number of samples should be sufficiently large, and the third condition was that each sample should have 30 or more data points. So the sample should not be very, very small. And fourth condition was that an original population can have any distribution, normal or uniform or exponential or gamma distribution, etc. But some distributions which are rare as such, like Cauchy distribution, which have infinite variance and infinite means, etc., then those kind of distribution will not give a bell curve when I find the distribution of means from various samples. But apart from that, if the conditions is satisfied that the means and the variance of the original population are finite, if the number of samples which I take is sufficiently large, and if each sample contains 30 or more observations, and if these observations are independent from each other, so in that case, the sample means are always distributed along the bell curve. That is what central limit theorem says. So here we did one thing, that we created one population like this. Now that population is of 1000, not 1000, but actually 100,000 observations, right? And it is following deliberately. I have taken a non-normal distribution, so that is a gamma distribution, right? And then we create some sample size 30. So as the central limit theorem says that any sample size which is 30 or more, that is fine. That is number of observations in each. And then we took number of samples, because from these as such you can take so many samples of size 30, right? But we don't want to, or rather we want to test our central limit theorem for around minimal number of samples. So I said here that number of samples should be large, but large does not mean some thousands of samples are required, some 50 to 100. Okay, so we start with minimal number of samples, that's 50 samples. We initialize one empty list which will store the means of all these 50 samples, and we initialize another empty list which will store the confidence interval with which the means are calculated, right? And this is the code to generate that mean and the confidence interval. I want a confidence interval of 95% accuracy. So from earlier Z table, 95% means Z score is 1.96, and the formula for calculating that sample mean is found by this thing. Sample mean is equal to the confidence interval formula is sample mean plus or minus Z score into sample standard deviation divided by square root of n, where n is the number of observations in the sample. So we are using that formula only. Now we know that for 95% of the confidence interval, the Z is 1.96. Okay, so then in that case, you will directly use that value in this formula. That is this formula. So this is that Z multiplied by standard deviation of the sample sigma, which we have separately calculated by np.std. And since it is for sample, I am writing degree of freedom is equal to 1 divided by square root of sample size root n. Okay, that gives multiplied by the Z score. That gives me confidence interval, and then each mean, whenever I calculate, then each mean is given a interval like value of that mean minus this much value, or value of that sample mean plus this much value. So that is that x bar plus or minus plus Z into sigma divided by root n, and x bar minus z into sigma divided by root n, right? So that is the interval. And when we calculated that interval, actually we got one this kind of result, that these are my means. For example, first two means, this is my confidence interval in this, for this particular case, and therefore these are the, this is my CI, and therefore these are the values of the intervals in which my means are located. Because if this is the mean, but that is not 100% accurate, because it is 95% confidence. So actually I can just say that my mean is located between these two values. Similarly, when I say this is the mean for the second sample, that means when I do plus or minus this, then that mean is located between this or these values, okay, and so on. And we also plotted this graph, right? And I said that these means actually follow normal distribution. So many people are not clear about that, but for observing that, what you will have to do is you will have to plot a different plot, right? And how will be that different plot plotted? Then you will take one x-axis, one y-axis, one x-axis. One will be your that 4, which was the final mean, true mean 4, okay. Then some observations. See this dotted line, that is your true mean, that is the mean of all these means of 50 samples, right? And then some observations which are below the true mean, below the red colored line, they will be plotted on the left side here, okay. And some means which are on the, which are above that red colored line, they will be plotted on the right side, right? So this thing. This way. And then if you plot a smooth curve passing through them, then that would be nearly a normal distribution. That is the meaning that means are normally distributed, correct? So here I have plotted that curve using the additional code. So this is that additional code, histogram and KDE plot. And for KDE plot, we know that Matplotlib cannot plot KDE plot. We have done this step so many times, so I'm not wasting time in that. But KDE plot is plotted by SNS library, and you can see that this is the perfect normal distribution, perfect red color, and this is the normal blue colored is the normal distribution which is given by my sample means, okay. And this is that 4, here somewhere is that 4. So you can see that slightly shifted values are there, but more or less central limit theorem is obeyed. And this is just 50 samples are taken, and each sample is having 30 observations. Let me take each sample is having 300 observations. Then you will see that now this is shifted more close to 4, right? The blue curve, which is the sample means distribution, that is shifted very close to 4. In fact, it has gone slightly on the higher side, right? And if I similarly get more samples, instead of 50 samples, if I take 100 samples, then you will see that now this peak of the sample distribution is exactly at 4, almost exactly 99%. I can say that central limit theorem is obeyed, right? So that is what I wanted to display. That much was left with previous lecture. Now we want to start with this lecture, that is hypothesis testing, okay. Now this hypothesis testing is the heart, soul and the brain for a data scientist, okay. So we start with one example only, our familiar example in A/B testing. So A/B testing is that when two different websites are made by two UX designers, you are suppose running a large e-commerce portals, and you want to further optimize the conversion of the client from the moment he logs in to the moment he makes his purchase and checks out, okay. Everything should be done in quick clicking and in very smooth manner, and we know that that can be measured by something which is called click-through rate. So this is first design A, and this is another design B, and these are my click-through rate for first and for second, right? So suppose the sample mean from the, suppose the CTR of design A is hypothesized to be higher than CTR click-through rate for this. So that becomes my null hypothesis. That means whatever you assume initially, that is your null hypothesis. That click-through rate for first design is higher than click-through rate for second design. Then whatever is its reverse result, that is called alternative hypothesis. So alternative hypothesis is that click-through rate for first design is not higher, not greater than. That means it is less than or equal to click-through rate for second design. So suppose first design is my existing design, this is already having, and this is the proposed design. So if I get my null hypothesis correct, then only there is a point in changing the design, right? Because if I change the design and the click-through rate remains less than or equal to, not greater than means less than or equal to. So either my click-through rate decreases or that is my click-through rate of A is less than or equal to, or it remains the same as B, then I will say that that is my alternative hypothesis. So that is what I actually want, right? That CTR, click-through rate for A, should be less than click-through rate for B. So in that case, I would say that B design is better than the A design, right? So then I would go for B design. So if this, forget about that equal to case, because if it is equal to, then also I will not bother to change my UX. But if it is less than, then the original design has less click-through rate and the new design has more click-through rate. So in that case, I will say that alternative hypothesis is correct, and therefore I will go with the proposed design. Okay. So this is a very daily, business example of this hypothesis testing. Now, how to do this? Then first, it is hypothesized that click-through rate of A is higher than click-through rate of B. So that is what I said here, right? Then sample means of click-through rate from both designs will follow normal distribution thanks to central limit theorem. So we are going to do a lot of detailed discussion about hypothesis testing, and every time I will not speak these sentence, but you should understand in each of that case which we are going to describe in detail that the central mean of both follow normal distribution. That is the root, or that is the root cause or root reason why I can do hypothesis testing. So hypothesis testing is made possible thanks to which theorem? Central limit theorem. So you can perform a hypothesis or two sample t-test, okay, to determine if the difference in means is significantly higher. So what you will do is you will take multiple samples from this design and find the click-through rates, and then you will take multiple samples from this design and find click-through rate and plot the mean click-through rate on the same graph paper. So if you plot it, and suppose for the A design you get this kind of, sorry, this should be code. For A design, you get this kind of, say, orange. And where is its mean? Then for normal distribution, central limit theorem says that this is a bell curve, right? So normal distribution means this is the mean click-through rate of all the samples which had designed A. And on the same graph paper, now I am plotting the graph for the other, okay? And suppose that graph comes out to be like this. So in that case, its mean is somewhere here. So that means mean click-through rate for the second design, B design, of all the 50 samples of the B design, that is higher than mean click-through rate from, so mu B is higher than mu A. So then in that case, I will say that click-through rate of B is higher, or that means A is less, right? But that means that A was poor design, and my proposal that I want to change the design to this B design, that is correct. So in that case, I will do this UI change. So A/B testing is called that the customers are exposed to both the websites. Few customers are exposed to original website and few are exposed to the new website. And this is usually a smaller sample initially, and it is decided that does the mean click-through rate increases? If it increases, then your alternative hypothesis is true, and then in that case, you will use this new UI, right? Okay. And what is the meaning of this two sample t-test? Because here there are two samples. You are taking your first set of samples, 50 samples from design A, and another set of 50 samples from design B, and you want to compare them. So that is why it is called two sample t-test. Okay. So use that two sample t-test and decide which hypothesis is correct. Now the question is, how to decide which hypothesis is correct? Do I have to take 50 samples each time? Do I have to plot the graph for each design, this design and this design, and then do I have to visually check which mean is higher? No. This Python has ready-made functions for two-way t-test. For example, here somewhere t-test one sample, that is one-way t-test. Okay, and similarly later on here somewhere there would be another code t-sample IND, that is for two-way two sample t-test. Okay, so that is, you can directly import that as a library or part of a library, and your code will do the analysis and give you directly the result. Okay, so earlier when this coding knowledge was not there, then statistician used to use key tables and Z tables and everything. Now fortunately all those things are not much required. Only a few basic information about Z table is required. For example, this much. Entire Z table was very complicated, I showed you. But if you just remember this many confidence intervals, then it is fine. Okay, there is no need. And as such also, nobody will expect you to remember the Z score. You can always look it up through the internet or that kind. Just like nobody expected that you will remember the logarithm of all the numbers, right? Similarly, nobody expects that you will remember the Z score. You can look at it. by Z table, which are readily available on the internet, or even you can take a printout of a good Z table and keep it with you. Okay, so that is what is about hypothesis testing. However, now we want to make a complete deep dive into hypothesis testing. So core concepts of hypothesis testing, in which these are the core concepts: what is null hypothesis, what is alternative hypothesis, what is significance level alpha, what is p-value, it should be small p, but that is okay, what is test statistics, okay, and what are different types of error. So this is something which are the core concepts about hypothesis testing, and I am not doing in this lecture because we will do it in next lecture, and then immediately you will follow it by some practical examples. Then only you will understand. Now the question is how to find whether, here I said that you don't need to actually visually plot the two curves, normal curves for the sample means, and then compare them and find mu b is greater than mu a, or it is not greater than mu a, and then reject or accept the null hypothesis like that. You just have to use the code, right? So we will take some examples, then you will realize that how code or results obtained by ready libraries in the Python, they help to accept or reject any hypothesis. So more important is the key concept and how many tests are there. Then there are several tests available in Python, like one sample t-test, two sample t-test, paired sample t-test, another is called ANOVA test, another is called chi-square test, and another is called correlation test. And for conducting all these tests, you don't have to take actually the sample, 50 samples, each of some number of observations and all that. There is absolutely no need to do all that exercise every time. You just import this test or this test or this test or this test, this or this from the suitable library. Most of the time it will be SciPy library, and just use that test which is available to you, right? So don't miss the next few lectures, otherwise you will never be a proper data scientist. You will just be someone who can code a bit and plot graphs a bit, and maybe mechanically do the train test split, and mechanically use random forest or XGBoost or decision tree or KNN or maybe say A-means or various kinds of algorithm, neural network, etc. But you will never understand the business aspect of the work of a data scientist. So all these examples which are taken here, all examples, each and every example is some real life example and data with actual business examples taken from different domains. So see you in the next lecture. Wait until then.